and head Department of Physics, Art and Commerce and Science College, Moregaon, Maharashtra. He is a master trainer in physics, metallurgy by the University Grants Commission and Ministry of Education, Government of India. He is the only professor from Amravati University to receive this honor. Thank you very much, sir, for accepting our request and delivering a talk. He has written large number of research papers. He has done PhD guidance, the PhD students, and he's doing large number of research papers and research publications in different national and international journals. Thank you very much, sir. We have with us our Honorable Shri B.N. Dixit, our Director Legal Metallurgy, sir, who has done a lot in the field of legal metallurgy during his tenure. We got large number of laboratories established at the state and the central level, and that was an achievement which will always be remembered in his name to make the development in the field of legal metallurgy. Thank you very much, sir, for being with us and motivating us for doing good activities in the field of legal metallurgy. Thank you, sir. I would like to request you, sir, kindly speak two words and allow us to start this conference. Over to you, sir, please.
Thank you, Director Ashutosh Agrawal ji, Department of Consumer Affairs, Ministry of Consumer Affairs and Public Distribution. So you have given a lot of appreciations. So it is your kindness. Today the topic is on the nanoparticles and its influence for the measurement of the values and other things. That is the part of the metrology, and metrology plays a very important role in various fields of the life. So that covers many things. So in the Legal Metrology Act, the base units has been defined. On the basis of the base units, so various parameters are being defined in different fields. So today topics is also related with that very fundamental base units, and I hope that Dr. N.R. Pawar will guide us in best way that how to do its investigation and measurement of these nanoparticles and its influence. The topic is very important, and I hope that all the participants, the legal metrology officers, scientists, professors, and other people who are participating in these very programs, they will get the very good knowledge from Dr. Pawar. And I wish for the success of these very programs, and the things will be uploaded on the website of the Department of Consumer Affairs, and people will know about the subject and all those very things for a longer time. So today the Dr. Pawar presence is very important for us. He will speak on the investigation of these nanoparticles, and I wish for the success of the programs. I request Dr. Ashutosh Agrawal ji to request Dr. Pawar to speak on that very subject. Thank you, Ashutosh ji. Thank you.
Thank you very much, sir. Thank you very much for a kind and motivating words, sir. As you have already spoken, obviously after this program, the video and the PPT will be available on our website and so also on the YouTube channel. So the participants can be benefited even after the program. With the help, with the consent of Professor Pawar, I would like to request you, sir, kindly share me this PPT after the lecture so that I can put it on my website. And with your permission, we will also place the video of this today's recording on the YouTube channel as well as on our website. Thank you, sir. Thank you. Now I would like to request Dr. Pawar to kindly enlighten us with his vast knowledge and experience. Over to you, sir, please.
Thank you, sir. Thank you. Sir, my screen is visible?
Yes, sir. Very well. Please.
Yes, sir.
Yes, sir.
Thank you, sir. Thank you, sir. Very good morning, you all. Honorable, respected Professor Dr. B.N. Dixit, sir, and he is a former director of LM Government of India. With a deep sense of gratitude and pride, first of all, I would like to thanks Honorable, respected Professor Dr. Ashutosh Agrawal, sir. He is a presently director legal metrology, sir. I am very much thankful to you, and I am here because of our respected Ashutosh Agrawal, sir, and all the excellencies on this platform. First of all, I would like to say a few words about the methodology nowadays in the field of new education policy and the Indian knowledge system. Now, I am the master trainer of this, and the methodology is very important. And the aim of our Ministry of Education uh, to how to connect the traditional synthesis method of the material and the advanced techniques of the synthesis of the material, and it is a lot of advancements in the synthesis of the material in traditional system because these methods are mostly eco-friendly, and now the advanced techniques for the synthesis of the materials in various fields definitely they cause the pollution in our environment. Now the I will deliver a very innovative talk on the topic investigation of the influence of nanoparticles on the stability of the hybrid nanofluids. These are the contents of this talk. First, we discuss about the nanoscale nanomaterial, their classifications, nanoscience, nanotechnology, and a short history of that. And what are the factors cause the properties of the nanomaterial? And there are so many methods for the synthesis of this material. After then characterization, this is important part. Then nanofluid and again a hybrid nanofluid and how to cause the stability of this nanofluid in the base fluid like methanol, ethanol, ethylene glycol, and like that. And there are some applicable applications. And what is the sustainability of the nanoparticle? And it is our need because in NEP, the director of chairman of the NEP, Dr. Kasturi Rangan, he said that when we protect our environment, then definite every living organism will be survive in our universe. So the protections of the universe is very important, and that's why in the field of the material science, particularly for synthesis of number of types of the uh, nanomaterial and various materials, the sustainability is required for that. Nanoscale, it is used to refer to object which dimensions of the order of 1 to 100 nanometer. We are the familiar about this. Nanomaterials are the particles of metals, semiconductors, and insulators with size in the range of 1 to 100 nanometer, at least in one of three dimensions. The nanomaterials can be broadly divided accordingly to their degree of confinement. One dimensions, that is the nanowire, nanorods, nanotubes are like that. Two dimensions, graphene nanoplates, nanosheets. Three dimension, fluorine nanoparticles, etc. And zero dimension, that is our quantum dots that play very important role. Now these are some size comparison of the size of the nanomaterial. Now the classification of nanoparticle, that is important part here. Nanoparticles are broadly divided into various categories depending on their morphology, size, and the chemical properties. Carbon-based nanoparticles are the fluorine and carbon nanotube, represent two major classes of carbon-based nanoparticles. Fluorine contain nanomaterials that are made up of globular hollow case such as the allotropic forms of carbon. Due to their electrical conductivity, high strength structure, electron affinity, and versatility, this material possesses arranged pentagonal and the hexagonal carbon units. Metal nanoparticle. These nanoparticles are purely made up of metals due to well-known localized surface plasmon resonance, that is LSPR characteristics. These nanoparticles possesses unique optoelectrical properties. Nanoparticles of the alkali noble metals copper, silver, gold have a broad absorption band in the visible zone of the electromagnetic solar spectrum. Lipid-based nanoparticles. These nanoparticle contains lipid moieties and effectively using in many biological applications. Generally, a lipids nanoparticles are spherical with diameter ranging from 10 to 1000 nanometer. Polymeric nanoparticles. Lipid nanotechnology is a special field which focuses the designing and synthesis of lipid nanoparticle for various applications such as the drug carriers and delivery and RNA release in cancer therapy. Ceramic nanoparticle. Ceramic nanoparticles are inorganic, non-metallic solids synthesized via heat and successive cooling. These nanoparticles are getting great attention of researchers due to their use in applications such as the catalyst, photocatalyst, photodegradation of dyes, and imaging applications. The semiconductor nanoparticle. This nanoparticle possesses a wide band gap and therefore shows a significant alternation in their properties with band gap tuning. They are very important materials in photocatalyst, photo optics, and the electronic devices. Now, what is the nanoscience? It is an emerging area of science which involves the study of materials at the nanoscale that we have discussed. Nanotechnology, the researchers develop and apply materials at nanoscale to develop a new product or methods, that is tuning nanostructure into usable tools, turning nanostructure into usable tools and applications. It is a technology of design, fabrications, and applications of nanostructure material. Nanotechnology is likely to have a profound impact on our economy and society in the early 21st century, comparable to that of semiconductor technology, information technology, or cellular and the molecular biology. Nanotechnology involves the manufacturing and the applications of instruments and materials that have unique properties because of their small size. Researchers are using these unique properties of materials at this small scale to create new and exciting tools and products in all areas of science and engineering. These are the nanoparticles, and this is the nanotechnology. By using these nanoparticles, nanowires, we have synthesized the number of materials like that, and these materials are used in our daily life. That is a nanotechnology. Now, the history of nanotechnology. First, Professor R. Feynman, Californian Institute of Technology, delivered a first talk in 1959 at the session of the American Physical Society. In this lecture called "There is a lot of space down there." For the first time, the possibility to create a nano-sized product with the use of atoms as a building particles was considered. And this talk play a very important role for the origin of the nanotechnology and especially the material science. The word nanotechnology was introduced for the first time into a scientific word by Yan Taniguchi at the International Conference on Industrial Production in Tokyo in 1974. In the second half of 1980s to the early 1990s, a number of important discoveries and inventions was made. And now in 2000, the Japanese Economic Association organized a special department of nanotechnology. In 2001, the National Nanotechnological Initiative, that is NNI of the USA, was approved. And recently, nanotechnology research being in the CIS countries usually within the framework of state scientific program. And nowadays, in every big universities and national institutions and affiliated college, the research on the nanotechnology, material science is going on. But what is the history of the nanotechnology? Nanotechnology is not a new. Gold nanoparticle in glass are reflected as a red, and this was found in ancient time. In ancient times, stained glass makes know that when we put finely gold or silver in the glass, they would get beautiful colors like that. They use the nano size gold and the silver particles since optical property change with the nanoscale. So this technology is not a new. It is a very old technology, ancient technology, but it was invented basically in from 1974 and onward, and now there are a lot of advancement of this nanotechnology and the material science in every field of the research, every field of the, and there are a lot of application in various field of this type of the technology. Gold and silver nanoparticles were used as a pigment to attain color in glasses in 17th century. And like this is also we are the familiar. The cup exhibits the red color with lit from the behind and green when seen in reflected light from the front side. These are the various products, and these products are based on our nanotechnology. Now, important thing is that what are the principal factors cause the properties of the nanomaterial? How the nanomaterial differs their properties as compared to their bulk material. At nanoscale, the properties of materials are very much different from those at the large scale. Two principal factors cause the properties of nanomaterial to differ significantly from the other material. And the first thing is that is increased relative surface area. And second is a quantum confinement effect. These two parameters play very important role for the advancement in the properties of the nanomaterial. These two factors enhance properties of the nanomaterial such as the reactivity, strength, and the electrical characteristics. And how the size effect of the nanomaterials. If we consider the side here, sides are 3, and so the volume equal to area cube. We are the familiar, and basically this topic is a prepare for the research scholar and the students. Okay, and they how to understand the size effect of the nanomaterial. If the sides are 3, then surface area is a 54, then volume is a 27, surface area to volume that is 2. But when we reduce the size, side is a 2, then surface area to volume ratio increases, that is 3. Again we reduce the side, that is we reduce the size of that material, then side is a 1, volume is a 1, then surface area to volume ratio is 6. So this factor play very important role for enhancement in the properties of the material. This is the first cause of the nanomaterial. What here? Surface area to volume ratio increases. Definitely number of particles comes on the surface for the interactions, especially in chemical interactions. So many types of the interactions. If the number of particles are participated in the interaction, definite there is enhancement in the optical, physical, and other properties of that material. And this is the beauty of the nanomaterial. Surface area to volume ratio, again surface area, that is if we consider the spherical nanoparticle, then surface area is a 4 pi r square and volume is a 4 by 3 pi r cube, and then what here, that is a 3 by r. So the surface area to volume ratio is directly proportional to the 1 by r, that is inversely proportional to the radius, that is diameter of that particle. Large surface to volume ratio proportional to the inverse of the particle size, basically we consider the radius or the diameter of nanoparticle, changes the role played by the surface atom in determining their properties. If we consider size of the cube is 1 meter, then collective surface area is a 6 meter square. And again we reduce the size of that cube 0.1 meter, then surface area increases, then 1 centimeter, that is a 0.01 meter, then surface area is 600 meter square, and like that when we reduce that in a nano size, that is a 1 nanometer, then the surface area is a 6,000 kilometer square. Now we consider this one of the example. When we reduce the size of 1 meter up to 1 centimeter, then surface area is a 600 meter square, and that is nothing but the 6 running tracks of our this cricket pitch, like that. So we confirm here how the surface area to volume ratio increases or surface area increases by reducing the size of the material in nanoscale. And second parameters or second factor, that is the quantum confinement. As the particle size decreases, the electron becomes more confined in the particle. As a result, valence band, that is the field orbital bands, we know, and conduction band, that is empty orbital band, break into quantized energy levels. When the atomic orbitals of nanoparticle become discrete or quantized, quantum confinement occur. Quantum confinement is the restriction of the electron moment. Quantum confinement is achieved when electrons remain below the Fermi energy, that is EF. So the quantum confinement makes it possible to fabricate materials with tunable electrical and optical properties, which can result in the development of new devices. So these factors play a very important role for the enhancement or the advancement or to change the properties of the nanomaterial as compared to their bulk size. Quantum confinement and the surface area to volume ratio play very important role for the development of the new devices based on the nanomaterials and the nanotechnology. Now some properties of this material, that is also the important topic. And what is that? Okay, mechanical properties. That properties improve hardness and toughness. 1 minute. Sir, 1 minute. There is overlapping of one slide. Exactly. Okay. And this is the one slide of the carbon nanotubes. And we imagine here what is the strength and great tensile strength of this carbon nanotube. Now this is the carbon nanotubes. We can uh, synthesize the materials, okay, by rolling by and like this, okay, by using the strength of the carbon nanotubes. And now synthesis of the nanoparticle mostly with the two types of the methods, that is the top down and the bottom up approach. In top down approach, nanoscale objects are made from larger objects. Integrated circuit fabrication in an example for top down nanotechnology, and this is the one of the technology. In some applications, larger scale materials are grinded to the nanomaterial scale, because the grinded machines are available nowadays, and this is a top down technology, big to small. Second is the bottom up approach, that is the small to big, making larger nanostructure from smaller building blocks such as the atom and molecules. Manufacturing of carbon nanotubes using a metal catalyzed polymerization method is a good example of bottom-up approach of nanotechnology. And again, these approaches further divided into various subclasses based on the operations, reaction, condition, and adopted protocols. Okay. Then again the top-down synthesis. Now in this method, destructive approach is employed starting from larger molecule which decompose into smaller unit, and then these units are converted into suitable nanoparticles. This is just we have discussed, that is the milling or the grinding. Then CVD, physical vapor decomposition, PVD, and other decomposition techniques are the top-down synthesis. Then bottom-up synthesis, this approach is employed in reverse as the nanoparticles are formed from relatively small substances. Therefore, this approach is also called a building up approach. And these are the some technologies that included the sol gel, green synthesis, and spinning, and the biochemical synthesis, and like that. Now, various nanosynthesis methods, especially in affiliated college and the universities and the national institutions, we use this type of the methods for the synthesis of the nanomaterial. Then these methods are physical methods are ball milling, thermal evaporations, and like that. Then chemical, solvent processing, co-precipitation, microemulsions, hydrothermal synthesis, chemical vapor decomposition, and like that. And the biological synthesis, this synthesis techniques play very important role, because we have synthesized the nanoparticles or the nanomaterial without without any nano pollutions, because when we synthesize the nanomaterials by using the chemicals method, definite there is a nano pollutions. But nowadays, to protect our environment, it is essential to control the nano pollutions and the various types of the pollution for the synthesis of the materials. So the plant extracts and the biological methods are mostly the eco-friendly method, and during that there is no any nanopollutants, and so we synthesize the material by using natural resources, that is a plant extract, and like that. Okay. And one of the professors, I think basically I don't know, is belongs from a very big university. He has synthesized more than 300 nanoparticles, including the gold and the silver nanoparticle, by using the plant extract. And for the synthesis of that material required only the 30 minutes. And nowadays it is essential such type of the technology, eco-friendly technology, for the synthesis of the any materials for the um, for the to protect the pollution our environment, and basically to stop the water pollution, soil pollutions, and air pollution, various types of the pollutions. Because if we are the researcher, it is essential to think about the pollutions, because now in our capital, as think today, the एयर पोल्यूशन जो हम दैट इज जो हम लोग कंपोनेंट्स बोलते हैं पीएम, दैट इज 260 अबाउट. And as per the guidelines given by the monitoring institutions of the government of India, our requirement is only the 2.5. So as a researcher and the faculty member, as a responsible person of the society, it is essential to think such type of the pollution and how to stop such type of the pollution without stopping the industrialization, without stopping the synthesis of such type of the novel material. And these are the chemicals method, that is the co-precipitation, solvent processing, microemulsions, hydrothermal, and like that. All these are the chemicals method. And this is a very simple method because mostly due to the insufficient infrastructure, mostly the affiliated college use this technology, soil gel processing. Now it is a very simple. Soil is converted into gel, and this is the technology here. Metal oxides and metal chlorides are typically undergo hydrolysis and polykondensation reactions, generating this bond like this. Yeah, metal oxygen metal or metal hydroxide metal polymers in solution that we form the gel. After drying process, the liquid phase is removed from the gel, and then by thermal treatment, that is a calcinations enhance the mechanical properties, and like that we have synthesized the number of nanoparticle by using this sol gel synthesis. That sol converted into the gel, then it is a dried, and after then this shifting and then grinding, and like that. This is a very simple technique. And then bottom up techniques that we have discussed already here, that is a sputtering done under the high vacuum can be used to form thin film of metals and non-metals such as the metal oxides. And second is a bottom up techniques, vapor liquid solid techniques, that is VLS. Okay, I'm not interested to discuss in detail here. Second is the synthesis of TiO2 nanoparticles, that is also the bottom up techniques. Basically what happened here, this thermally converted to graphene, and then graphene patch SS photo excited electron from TiO2 and shows down charge recombinations. And this is a techniques again just we have discussed, that is okay. And synthesis of alpha alumina. Okay, basically this is also synthesis by the Sol-Gel techniques. Nanoparticles of alpha alumina prepared by the Sol-Gel method from aluminum isoperoxide and aluminum nitrate. Starting solution was prepared by adding aluminum isoperoxides gradually in zero point 0.2 mole aluminum nitrate, and solution continuously stirred for the 48 hours. Later sodium, that is the SDBS, was added and stirred for 1 hour. Now this solution were heated up to 60 degrees and stirred constantly for evaporation process. The paste obtained was heated at 90 degrees Celsius for 8 hours, and then we get the nanoparticles, okay, in powder form. This is the synthesis of the silicon carbide nanoparticles. Okay, this is also we have synthesized by the solar techniques. Okay, second is a Boehm nanoparticle. This nanoparticle play very important roles, especially in various types of the various for the various applications in the various fields. And this is also we have synthesized. And one of the students awarded PhD on this topic, my research scholar. And then silver nanoparticle. The silver nanoparticle was synthesized by the thermal decomposition method at 700 degrees Celsius. Then this silicon dioxide nanoparticle, and now this nanoparticle we use for the synthesis of the hybrid nanofluid, because we know we are the familiar with the nanofluid. When we disperse the nanoparticle in the base fluid like methanol, ethanol, glycerol, then that can be converted into the, that is nothing but the nanofluid. But when we take the two nanoparticle, and these two nanoparticle, two types of the nanoparticle disperse in one of the base fluid like glycerol, then that can be converted into the hybrid nanofluid by using the various technique, by stirring, magnetic stirrer, and like that. Now this component we have synthesized the silver nano, the synthesis of SiO2 nanoparticle. This nanoparticle were synthesized using Sol-Gel technique for 10 minutes, 20 milli of water, and add 100 milli of ethanol are mechanically mixed. The next 2 hours see the dropwise addition of TOS. The pH is then raised to 12 by adding ammonium hydroxide. After that, the solution is heated to 70 degrees and agitated for the next 5 hours at 100 rpm. The gel is centrifuged 3 times using ethanol. Next 24 hours, the solid is heated to 90 degree. The material is then crushed to produce nanopowder after being calcined for 24 hours at 500 degree. Then this nanoparticle also used for the synthesis of the hybrid nano fluid. These ZNO nanoparticles were synthesized using the co-precipitation method, because we have discussed the number of times the number of nanoparticles synthesized by the Soldier techniques. So we have to synthesize this type of the nanoparticle by using some other techniques. Now 100 millimeters of water are combined with 15 grams of zinc acetate uh, dihydrate, and the mixture is a magnetically stirrer. Now 2.7315 gram of this sodium hydroxide is added to the previously made solution after being dissolved into 50 milli of water. Then the mixture is heated for 4 hours while being agitated at 100 rpm. Ethanol is centrifuged 3 times. Then the substance is heated to 100 degree for a full day. Then ZNO nanoparticle are obtained by crushing the solid that has a form. Then again, this nanoparticle also we use for the synthesis of the hybrid nanofluid. A solution was prepared by dissolving 6 grams of this ZrO2 in 100 milli of distilled water and stirring it continuously for 1 hour. Separately, 1.0357 grams of sodium hydroxide was dissolved in 50 milli of water, and this alkali solution was then added dropwise to the previously prepared solution, and the resulting mixture was then heated and stirred at 70 degrees Celsius for 5 hours to facilitate the reaction. After the reaction, the suspension was subjected to centrifugations for 10 minutes, and this washing step was repeated 3 times to ensure the purity. The collected material was subsequently dried by heating at 90 degrees Celsius for 24 hours. Finally, the dried solid was ground into a fine powder to obtain this ZrO2 nanoparticle. Now, these 3 particles we use for the synthesis of the hybrid fluid by using the various types of the base fluid, ethanol, methanol, glycerol, and like that. Now, we have synthesized the nanomaterials. Now, what are the characterizations of these nanoparticles? There are different characterization techniques have been available to analyze the various physiochemical properties of nanoparticle, and mostly these are the X-rays, that is the X-ray diffraction, that is called XRD, then XPS, IR, same, TAME, and like that. Then morphological characterization. The morphological features of nanoparticle always attain great interest in morphology, influences most of the properties of the nanoparticle. There are different characterization techniques that we have discussed here. Basically, the same technique is based on the electron scanning principle, and it provides all available informations about the nanoparticle at nanoscale level. We use this technique to study not only the morphology of the nanoparticle but also the dispersions of nanoparticle in the bulk or matrix. The structural characterizations are of the primarily important to study the compositions and nature of bonding materials. It provides diverse information about the bulk properties of the subject material. XRD, then EDX, XPS, IR, then Raman, Zeta size analyzer are the common technique used to study the structural properties of the nanoparticle. XRD is one of the most important characterization technique to reveal the structural properties of the nanoparticle. It gives enough information about the crystallinity and phase of nanoparticle. It also provides rough idea about the particle size through the Debye-Scherrer formula. This techniques works well both single and the multiple nanoparticle identifications. In case of smaller nanoparticle having size less than 100 of atoms, the correct measurement of structural and other parameters may be difficult. Moreover, nanoparticles having more amorphous characteristics with varied interatomic length can influence the XRD diffraction. TAME, a device, it is widely used to know about the elemental composition. This technique used for the determination of the elemental compositions of the material with a rough idea of weight percent. The electron beam focus over a single nanoparticle by SAME or TAME through the program functions to acquire the nanoparticle under the observation. Nanoparticle comprise of constituent elements and each of them emits characteristic X-rays by electron beam uh, irradiation. The intensity of specific X-ray is directly proportional to the concentration of the X-split element in the particle. This technique is widely used by researchers to give support to SAME and other techniques for confirmation of their element in prepared material. Same surface morphology, particle size determination, and the shape. This is the same. And how it is a differ from the TAME. Now, TAME, we detect the internal structure like this. Here we observe this type of the picture by using the same, by using this TAME, and the particle size is like this in a TAME, and in same the particle size are like this, and then shape like this, then the crystal or atomic structure we obtain by using the TAME and like this. And this is the difference between these two morphological characterization. EDX techniques used to determine the positions of nanoparticle. XPS is considered to be most sensitive techniques, and it is widely used to determine the exact elemental ratio and exact bonding nature of the element in nanoparticle materials. It is a surface sensitive techniques and can be used in depth profiling studies to know the overall compositions and compositional variations in the depth. It is based on the basic spectroscopic principle. Vibrational characterization of nanoparticle is normally studied by FTIR, Raman spectroscopies. These techniques are most developed and feasible as compared to other elemental analytical method. The most important range of nanoparticle is the fingerprint regions would provide significant information about the material. The degree of functionalizations was revealed from the FTR bonds. Then again these are the again more morphological techniques. Okay, and then optical characterizations, it gives informations about the absorption, reflectance, luminescence, and the photophosphorus properties of the material. It is widely known that nanoparticles, especially metallic semiconductor, possesses different colors and therefore best harmonized for photo-related applications. It is interesting to know the value of absorptions and reflectance of this material to understand the basic mechanism for each applications. Then UV and like that, these are the techniques. Then again the optical characterizations, and now the analysis of the nanomaterials. We have synthesized the material, and then we discuss about the various techniques for the determinations of the morphology of the material, synthesized materials. Now the analytical of analysis of these materials by using the various techniques. Mostly we use this XRD and like this. Then we obtain the grain size of the material, then thickness, crystallized phase, and then UV to determine band gap using absorption spectra and like that. Now what is the XRD? X-ray diffractions. Mostly it is a non-destructive technique used to analyze the structure of the crystalline material. It is the way of the study of the crystal structure is used to identify the crystalline phases present in a material and thereby reveal chemical composition information. Mostly, we have synthesized the number of nanoparticles, okay, and the average crystalline size has been calculated or has been computed from the XRD pattern by using the Shearer formula, and that is this formula is like this. And now just we have discussed what is the uh, background of the X-ray diffraction pattern for the various types of the materials, or the what is the um, pattern of the various type of the XRD pattern of the various types of the material. This is the XRD pattern of a single crystal specimen, and the single crystals are like this. Single crystal, then periodic across the whole volume. The XRD pattern of such type of the material is often like this. Then the XRD pattern of amorphous or liquid specimen, we often like this because these materials are not periodic, and then the XRD pattern is like this. The XRD pattern of gas molecule, the gas molecules are widely separated from each other, so their XRD pattern, if you observe, it is often like this. And now, what is the B? B is the width of this highest peak. We consider the highest peak, okay, and from that we obtain the width, that is a B, and B is equal to half of this 2 theta 2, sorry, 2 theta 1 minus 2 theta 2, that is a theta 1 minus theta 2, then we obtain a B. We consider the highest peak, the highest peak intensity. In next slide we will discuss in detail. Okay, this is the XRD pattern of alpha alumina. We have synthesized this type of the materials, nanomaterials, and this XRD pattern of alpha alumina nanoparticle compare with the JCPDS file number 711127. This file is exactly matched with our XRD pattern, so we consider that our synthesized material is a superior for the research. It is seen that the alpha alumina nanoparticle is well crystalline in nature, and the estimate size of alpha alumina nanoparticle using that Debye formula that we have discussed, that is 20 to 30 nanometers. This is the XRD pattern of Boehmit nanoparticle, and it is this XRD pattern is also exactly matched with the available XRD pattern, mostly in the JCPDS file number 0211307, and this is also the XRD pattern of the silicon carbide. This nanoparticle applicable in mostly in agriculture field, and so here also the pattern is also exactly matched with this available pattern in available literatures. This is the XRD pattern of the ZNO, and this nanoparticle we use for the synthesis of the hybrid nanofluid. The peaks were observed here. Okay, the crystalline size calculated according to that formula, and that found to be this. Okay, and uh, then it compare with the available data. The our XRD pattern is exactly matched with the available pattern. This is the XRD pattern of the ZRO2. Again, we observe that this pattern is also matched with the available data, that is a ICDD file number this 0030640, and this is the XRD pattern of the SiO2 that also observed. Now, how can we find the grain size of that material? We consider the highest peak, highest intensity. Okay, then we consider this position, that position of the theta. This is the theta, and now that data of the maximum peak, the value of the theta and 2 theta, this is the position theta, and this is the intensity and theta, and we consider the maximum intensity. I think this is at a 35, this is a 35. Now we consider these values for the calculation of B that we have discussed in Debye formula, that is the width of that. And now these parameters or these values, crystallographic refinement software, there is one software, that software is the crystallographic refinement software, and we often by putting these values in that software, we obtain the lattice parameter, interfacial angle, lattice constant, and the phase identified by using this software, by considering the maximum peak of the XRD pattern and the related value. This FTR technique, it is a technique used to obtain an infrared spectrum of absorption or emission of the nanoparticles. It is a simultaneously collect high spectral resolution data over a wide spectral range. FTR spectra were recorded by using this Perkin-Elmer FTR spectrometer spectrum to in solid phase using the KBR Paler's FTR spectrometer spectrum. This is the FTR spectra of the Bohr-Mid nanoparticle. And again, this FTR spectra is exactly match with the available literature value or the available literature spectra. FTR analysis indicate the vibrations of the metal oxygen groups, and this spectroscopy shows the degradation phases and the absorption in different regions, which indicates structural relationship between them. The inorganic groups is gradually decomposed at 735.47 centimeter inverse, and here and here also the absorption peak observed at this and this are very weak band at about this is attributed due to the symmetrical structure stretching vibrations of this nitrogen and the oxygen group, which might have come from the nitrate of the starting material, and the spectrum shows a peak at which due to the aluminum and the oxygen vibrations in a spinel block alumina structure. Similarly, this is the FTI spectra of alpha alumina. That is also the exactly match with the literature value, and because of the time restrictions, we have introduced here in my presentations very few FTR spectrum of the nanomaterials. Now this is the same. It is a techniques that produce the images of a sample by scanning the surface with a focus beam of electrons. The electrons interacts with atom in the sample, producing various signals that contain information about the surface morphology. And these are the same images of alpha alumina nanoparticle that alpha alumina nanoparticle used for the synthesis of the nanofluid. The crystalline looks like having a sharp surface edges as well as crystalline grains, and the particle foam-like morphology can be formed from highly algorithmated crystallites. It is confined that the crystalline sizes are nearly equal for all the samples, and this is the same images of the Bohr-Mid nanoparticle. Here also the crystal lights look like having a sharp surface edges as well as the crystalline grains, and the particles foam like morphology can be formed from highly agglomerated crystallites. It is confirmed that the crystalline sizes are nearly equal for all the samples, and these are the TAME images of few samples, and this is the TAME image of SiO2. From the TAME images, it was observed that the 1 minute, okay. These are the TAME images of the ZNO nanoparticle, and these are the TAME images of the SiO2 nanoparticle. Okay, and now the size distribution was evidently broad, and the diameter of the middle portions were 30 to 50 nanometer. The mean particle size was found to be this 53.472 nanometer. And here these are the TAME images of the ZNO nanoparticles, and these are the TAME images of the alpha alumina nanoparticle. Now the TAME micrographs of alpha alumina powder obtained from the solution combustions of aluminate nitrates and ultra fuel. It shows that most crystallities exhibit hexagonal platelet morphology. Some spherical particles were observed. The mean particle size was found to be 30 nanometer. These are the TAME images of the ZRO2, and the average particle size calculated about 22.75 nanometer. Now UV of some this synthesized material, and we are the familiar with the UV because this is a very common parameters, and the spectrum is shown above, spanning a wide wavelength range from this 250 nanometer to 950 nanometer, which include the UV visible and NIR regions, and then the absorbance is comparatively high in UV range, peaking at this with a value of this. This indicates the presence of defect states of impurities such as oxygen, the vacancies or metallic contaminants that introduce electronic transitions within the large band gap of this SiO2. It is a predicted transparency in the visible and the near infrared spectrum is confined by this absorbance's sharp decline beyond 400 nanometer. However, surface scattering or residual flow may cause slight vibrations. And this is the UV of this ZNO. This is the UV of ZrO2, UV of alpha alumina, and TG analysis. Now, here, this analysis play very important role, especially for the stability and to know the contents of that material. Figure illustrates the thermal degradations behavior of ZNO nanoparticles by representing the percentage of weight loss as a function of the increasing temperature. Mostly, TJ play very important role to represents the percentage of weight loss as a function of increasing temperature. The this TGA data reveal a gradual reductions in a weight up to 100 degrees Celsius during which a total 6.92% of the initial mass of loss that's shown here. In the subsequent temperature range, okay, an additional 5.96% weight loss was recorded. A significant weight reductions of approximately 21.81 was observed between this temperature range from 200 degrees Celsius to 350 degrees Celsius. Beyond 350 degrees Celsius, the rate of weight loss began to decline markedly. Between 350 degrees Celsius and 420 degrees Celsius, the sample experienced a comparatively lower weight loss, that is a 7.5% weight. This is a TGA analysis of the SiO2, and now here it is observed that initial weight loss 10.85 up to 150 degrees Celsius, which is a notably higher than that observed for ZNO nanoparticle over the same temperature range. In the subsequent temperature range of SiO2 nanoparticle demonstrated expectational thermal stability with only 3.95% additional weight loss. In order to study the thermal stability of the hybrid nanofluid or the nanofluid, this TGA analysis play very important role to determine the thermal stability of the hybrid nanofluid, and that's why uh, we have calculated or we computes or we measure this parameter of these nanoparticles. As the temperature increases from 400 degrees Celsius to 600 degrees Celsius, the TGA curve indicates a further minor weight loss. In the final phase between this, the weight loss further decreased to only this. And now the zeta potential. Now, this zeta potential parameter play very important role to understand the stability of the nanofluid, whether it is nanofluid or the hybrid nanofluid. So measurement of the zeta potential is essential in order to measure the or in order to understand the stability of the hybrid nanofluid or any types of the nanofluid. So, and if we measure these two parameters, zeta potential and the thermal conductivity, that play very important role to understand the stability of the nanofluid. If the stability is more, then there is a betterment or there is advancement properties of the nanofluid. Now, the thermal stability of the nanofluid play very important role, and nowadays nanofluid may be used as a coolants, okay, in industries and in our vehicles and everywhere, okay. If we increase the thermal stability of that material, defines the uh, It is depends on the thermal conductivity, because the thermal conductivity of any nanofluid play very important role to cause the stability of that nanofluid. This is the zeta potential analysis, or mostly we have synthesized this hybrid nanofluid. This is the uh, for the hybrid nanofluid. The zeta potential analysis, and we use here the base fluid, that is ethylene glycol. We use the ZNO. After ZNO plus alumina 3, alumina 2, alumina 1. Okay, alpha alumina. And now here, this is a zeta potential of the pure ZNO nanoparticle. This is the zeta potential of ZNO plus this. This is the zeta potential of ZNO plus this and ZNO plus this. Now the details also given here. Zeta potential this and this. The incorporations of alpha aluminum nanoparticle into ZNO nanoparticle significantly increases both zeta potential and electrophoric mobility with a smaller Al2O3 particle size, that is the 10 nanometer, leading to the highest value, indicating enhanced colloidal stability, that is indicating the good thermal stability, indicating the excellent value of the thermal conductivity of that material, or especially that nanofluid, and particle dispersions in ethylene glycol. This is again the zeta potential analysis of the nanofluid, and especially here we use, now in previous slide we use a okay. Now zeta potential analysis here, this is the SiO2 nanoparticle. In previous slide we used ZNO and the ethylene glycol. Now here our second combination is that is a pure SiO2. This is the zeta potential. Then zeta potential analysis of the pure SiO2 nanoparticle. Then in ethylene glycol, this is a zeta potential analysis of the SiO2 plus alpha alumina. Again SiO2, alpha alumina 2, 1, and like this. The addition of this alpha alumina to SiO2 in ethylene glycol increasingly enhance the negative zeta potential and electrophoric mobility, especially with smaller alumina particles, indicating improved colloidal stability and stronger particle repulsions. Now this parameter or this zeta potential analysis play very important role to obtain the colloidal stability or the thermal stability of the nanofluids or the hybrid nanofluids. And that's why we measure the zeta potential. Now it is observed that there is enhancement in the colloidal stability as compared to the colloidal stability with the ZNO of this alpha alumina in ethynyl glycol. Again here, this is the pure ZRO2. This is the zeta potential analysis of this. And now again here, okay, this is a ZRO2 plus alpha alumina 3 to 1. And we have synthesized the hybrid nanofluid by using these two nanoparticles, materials in powder form, nanomaterials in the powder form, ZRO2 and the alpha aluminas mostly. And we have dispersed these nanomaterials in the ethynyl glycol by using two-step method. We have synthesize the hybrid nanofluid, and then we measure the zeta potential of this hybrid nanofluid, and the analysis is here. The analysis is like that. Now what our result? Now this increases the magnitude of the negative zeta potential. Now the positive value of the positive higher or the positive higher or the positive plus or the negative value of the zeta potential, whether it is a positive, whether it is a negative, that is not matter. But the higher positive, higher negative value of the this zeta potential, that indicates the more stability of that nanofluid, that hybrid nanofluid. Now it is observed that zeta potential values are the negative, but the values are higher. If it is a zero, then the hybrid fluid is not stable. Mostly if it is a more than plus 30 minus 30, then as per our my understanding, if plus 30 minus 30 and beyond that, the value of the zeta potential represents the excellent stability of that nanofluid. Now this is again now second combinations. Okay. Now just here that we have discussed the same term and like this, all these things we have discussed previously. Now how to synthesize the nanofluid by using mostly we have synthesized the nanofluid in our research by using the two-step method, because the uh, by in two-step method, first we have synthesized the nanomaterials that we have discussed, whether it is the bone meat nanoparticle, silicon carbide, then alpha alumina, SiO2, and like that. We have synthesized such type of the material first. That materials are dispersed in a organic base fluid like water, ethylene, and like that. Then uh, the m- then that materials are stirrer. Okay, the mixers were stirrer by magnetic stirrer or by using the centrifugations, and that can be converted into the nanofluid. That mostly what here, two-step method is the most widely used method for preparing the nanofluid, because the nanoparticle first are produced as a dry powder by chemical or the physical method, and we have discussed the number of methods for the synthesis of these nanoparticles. We have synthesized such type of the nanoparticles by using the various techniques, and nowadays we focus on the synthesis of such type of the material by using the plant extract, mostly the eco-friendly techniques we use for the synthesis of this material nowadays. And now this nano size powder will be dispersed into the fluid, base fluid, in the second processing step with the help of intensive magnetic force, agitations, ultrasonic agitations, high shear mixings, or any one of that we may use. Then due to the high surface area and surface activity, nanoparticles have the tendency to aggregate. The important technique to enhance the stability of nanoparticle fluid is the use of surfactants. And now nanofluids of the nanoparticles are produced in the base fluid by two-step method by using a magnetic stirrer for 30 minutes. Mostly in our laboratory, we have synthesized the alpha alumina nanofluid and bone meat nanofluid by using the magnetic stirrer. And for the synthesis of the hybrid nanofluid, we use the uh, research laboratory of the Department of Physics, RTM, Nagpur University, and we synthesize the hybrid nanofluid by using the ultrasonication techniques for the stirrer. The mixture is subjected to microwave heating till the reaction is completed and the color of the mixture may change. The obtained product is the nanofluid. And thus we have synthesized the nanofluid by using this two-step method that we have discussed. In first step method, we have synthesized the material, nanomaterial. That nanomaterial dispersed in the base fluid, and mostly in for the synthesis of the hybrid nanofluid, we use the ethylene glycol. After then by stirrer, by using magnetic stirrer or the ultrasonications, and we obtain the hybrid nanofluid. Why use the two-step method for the synthesis of the nanofluid? Because in one-step method, the processes of drying, storage, transportations, and dispersions of nanoparticle are avoided. The agglomerations of nanoparticle is minimized and the stability of the fluid is increased. The one-step process can be prepare uniformly dispersed nanoparticle, and the particle can be stably suspended in the base fluid. However, there are some disadvantages of one-step method. The most important one is that the residual reactants are left in the nanofluid due to incomplete reactions or stabilization. And for that we use the two-step method, and these are some same images of the alpha nanofluid, and definite these images are completely different than the same images of these nanomaterials. Same images show the good dispersions of alpha aluminum nanoparticle in the base fluid. It is important for the qualitative analysis. We measure this by using this same images of Boeing nanoparticle. Also, by using this formulae, we may find this RO, okay, that is the size determinations, and it is also observed that the size of the dispersed materials in the base fluid is different than their original size, and hence we conclude that the synthesis nanoparticle is um, uh, excellent for the synthesis of the nanofluid. And second parameter, that is Brownian motions also play for the stability of the nanofluid. It is a erratic random motion of nanoparticle fluid as a continuous bombardment from molecules of the surrounding medium. It is a key mechanism governing the thermal behavior of the nanoparticle and fluid suspension. It enhances the effective thermal conductivity of the nanofluids. Now, just we have discussed about the zeta potential, because the zeta potential measurement, it is the potential, the zeta potential analysis of the hybrid nanofluid that we have already discussed. What is the role of zeta potential measurement in the stability of the hybrid nanofluid? It is that it is the potential difference across phase boundaries between the solids and liquid. It is a measure of the electrical charge of the particle that are suspended in a liquid. Zeta potential is a measure the stability of the dispersion formed due to the reaction. And these are some advancements of the nanofluid, because these nanofluids have high specific surface area and therefore more heat transfer surface between the particle and the fluid, high dispersion stability with a predominant Brownian motion of the particle, reduce pumping power as compared to pure liquid to achieve equivalent heat transfer intensification, reduce particle closing as compared to the conventional slurries, thus promoting system minimizations, and adjustable properties including thermal conductivity and surface weight ability by varying particle concentration to suit the different applications. Because of the time restrictions, I'm extremely sorry I'm not introduced here the measurement of the thermal conductivity. We have also measured the thermal conductivity of these materials, mostly the thermal conductivity of the hybrid nanofluids, and it is observed that the thermal conductivity play a very important role for the stability of the hybrid nanofluid, and that enhances the properties of the nanofluid. And we have also measured some acoustic parameters, just like ultrasonic velocity, after uh, then viscosity, and we also computes the theoretical value of the thermal conductivity by using this thermoacoustic parameter. It is seen that the experimental value of the thermal conductivity and the theoretical value of the thermal conductivity are exactly match with each other, and hence we conclude that our research is excellent for the further advancement in various fields of industry. Then applications of nanoparticle, we are the most familiar with all these nano size, okay, importance material in the development of novel nano devices, which can be used in numerous physical, biological, biomedical, and pharmaceutical applications. Nanoparticles have drawn increasing interest from every branch of medicine for their ability to deliver drugs in the optimum doses range often resulting in increased therapeutic efficiency of the drugs, weaken side effect, and the improve patients' complaints. Then there are so many nanoparticles. The nanoparticles have the lot of applications. Now applications of nanofluids. Now the research on the nanofluid. Okay, the further research on the nanofluid is required. Thermodynamical study of nanofluids applicable in power plants. Study of nanofluid could be used to provide cooling and lubrication actions and to control thermophysical and the biochemical properties of the material processing in drugs delivery system because colloidal form of drugs are easily absorbed by the body tissue and hence are more effective. Industrial cooling and nuclear systems cooling. In industrial cooling and the nuclear system cooling, the nanofluid play a very important role because have a good thermal stability or the have excellent value of the thermal conductivity. So enhancement in thermal conductivity is due to the stability of the nanoparticles in the nanofluid or in hybrid nanofluid. Nanofluids have high thermal conductivity and heat transfer coefficients compared to those of the conventional fluid. Nanofluids properties make them suitable for the next generation of flow and heat transfer fluid. Pioneering nanofluid research has inspired physicists, chemists, and the engineers around the world. And now, zeta potential analysis, okay, that already we have discussed. No need of all this. Then future work. The stability of the nanofluid or hybrid nanofluid is to be studied more comprehensively. The effect of the type of dissolving agents on the properties of the nanofluid is to be studied. The nanofluid prepared by two-step method is to be applied to a heat transfer system to find out the enhancement in the heat transfer rates. And now the sustainable nanotechnology, the need of that. The foregoing discussions lead the right to the definitions of the sustainable development, which according to the world's commissions of environment and development reports of 191987 is development that meets the need of the present without compromising the ability of future generations to meet their own needs. Then LCA is an invaluable tool for assessing the environmental impact associated with the entire life cycle of a product. In fact, it would be premature to make any claim on the environmental benefits of a product or manufacturing process without first considering its environmental consequence in a life cycle contains. It's a need to conduct life cycle based assessment as early in the new product development process as possible for a better understanding of the potential environmental and the human health consequences of nanomaterial over the entire life cycle of the nano-enabled product. Now, sustainable technology, matlab material processing, manufacturing, use, and the end of that life, that is also important. Now, I'm very much thankful because of the, I think our session is up to 12 to 20. I'm
Thank you,
very
sir.
much
Thank you
thankful
very
and
much.
acknowledge to Professor Dr. Ashutosh Agrawal, sir, Director of this Legal Metrology, Government of India. And with a deep sense of gratitude and pride, first of all, I would like to thank sir for inviting me on this platform. And I extend my sincere gratitude toward Professor Dr. Sanjay Yadav, sir, because of his constant efforts and the moral supports and the initiative. I am here, sir. Thank you, and I'm very much thankful to my best friend, okay, Professor Dr. Devraj Singh, sir. I acknowledge to all and thank you for your kind attention. And there is a missing of some parameters because of the time restrictions and the uh,